Okay, so today's plan is to finish section 3.3, finishing up chapter 3. This is measures of position. So we already talked about percentiles and such, and we're going to build on some of that today. We're going to discuss outliers and box plots. And then we'll start in on chapter 4. What I decided to do instead of trying to get together a supplemental video, say yesterday. I was kind of too sick Monday to really do much at all. But instead of trying to throw something together yesterday and then post it, and then like you'd have to decide whether you wanted to watch it really quick before this class or not, I think it's better to just continue on with regularly scheduled programming, and then I'll post a supplement for the next material, some of the material in chapter 4, and maybe also a little bit of material, kind of extra stuff from section 3.3, particularly with having to do with box plots and maybe different programming languages that you could create some graphics in, just for those who are interested. So maybe I'll post that material the next day or two, and then you can watch that. You have several days before our next class on Monday to kind of look over that material, and then we'll continue on with chapter 4 next time. So just so that I don't forget when we get there, I'm gonna pop the chapter 4 PowerPoints in the chat. Oh, sorry, I sent them as a direct message to somebody. It automatically, like, if somebody sends me a direct message, it automatically replies to them as a direct message. It like changes the scope. So okay, I think, yeah, I sent them to everybody now. There's 3 different PowerPoints. They're labeled with part 1, part 2, part 3 at the end. So those are in the chat. They're also available on Blackboard. Obviously, we're not going to do all 3 PowerPoints today, but this way you have access to them for chapter 4. And the quote of the day is actually from one of my wife's colleagues when she was working for a year in St. Louis, would say velocity is a vector quantity. And what she meant by that is it consists of both speed and direction. If you are working really, really, really hard, but you don't have a good direction, then you're kind of spinning your wheels and you're probably not getting a lot accomplished. But if you spend too much time pointing yourself in exactly the right direction, then maybe you never get started, you never get anywhere. And the way that I have kind of thought about this myself is, I guess being a math guy, I don't know, I have to turn it into an equation or something, that effectiveness equals efficiency times effort. So if I give 0 effort, if I want to learn something and I go and I research all of the best materials and collect all the best materials and, find all the most efficient ways to learn the thing. But if I never actually sit down and open the materials and learn it, then that's not effective at all. This is kind of my personal tendency. So it's something I struggle with, is like, okay, just get a good enough method and then actually get started. So some people call that like perfectionist procrastination, worrying more about the efficiency and never really getting started. And on the other hand, you have, the folks who are the like infinite energy kind of people, which is not me. But there are folks like that have just a ton of energy and just want to jump right in and get started. But if there's not a good direction, if you haven't looked at how to efficiently use that effort, you might be spinning your wheels there. So in something like, say, studying for an exam, or even just approaching a course or doing homework, anything like that, I think it's best to have some measure of both of them rather than really leaning heavily towards one or the other. Think about a little bit, how am I going to approach this homework set? How am I going to approach studying for this exam or writing this paper, right? Maybe it is a good idea to write an outline for your paper or to do a little extra research and how to efficiently write a paper. But then if you never sit down and actually start it, that's my issue, that's not good. That's not good either. So, setting deadlines for yourself that I'm going to just sit down and get something on the page. That's also, I think, in the much more tactical sense, in the much more shorter term, narrower scope sense, something important in math is if you get to a problem on the homework set and you say, hey, I'm looking at this problem and I don't see the strategy to get from start to finish, well, then maybe ask yourself, well, can I, so basically I can't find I can't find the end direction I want to go in. Can I like take a step in any direction, right? Can I write something down about this problem and maybe get me, one step further? Maybe it's a step in the wrong direction, but even with a step in the wrong direction, I might learn something that will help point me in the right direction. So that's a good, test taking strategy or problem solving strategy for more technical fields is, can you just get something written down if you're stuck? I mean, obviously, think about what the strategy would look like first, but if you're really stuck and you're like, I don't even know where to start, can you write something down? Can you write down a formula that applies to this situation? Can you even just kind of take, say, a word problem statement and just pull out the details in a less wordy way? And then as far as, career prospects and that kind of thing go, companies really care about the impact that you make. So that's one of the buzzwords these days is you want to have an outsized impact. So if you are extremely effective at, say, juggling wiffle balls, you know exactly the best way to learn how to juggle wiffle balls, and you've spent hundreds of hours mastering it, there's probably not too many people that are going to want to pay you to do that. So you also want to, in your job, I mean, of course, there are lots of, if you just like juggling wiffle balls, go for it. But if you're looking to further your career, make sure that the things that you're trying to become effective at relative to your job or your career are actually relevant to those areas. So this is how I think of impact, which it's kind of effectiveness times relevance. And that's one of the kind of buzzwords these days. Okay, so moving on to, or coming back, I suppose, to 3-3. And since it's been a week since we looked at this material, let's do a quick recap. If I don't have my little tablet thing set just right, then all of my writing goes one way or the other. So a quick recap. So we talked about first the measure of position or measure of relative standing. In 3-3, we're talking about the location or the relationship of a data point, a specific data point, or perhaps a data value relative to the data set. And we talked about percentiles. That was an important idea. We briefly talked about z-scores, but that's not going to really come up in what we're going to talk about coming up here so much. But percentiles, so if we say that data values or a data point is at the 90th percentile, what we mean by that is that data point has a value that's bigger than 90% of the data set and smaller than 10% of the data set. We mentioned there's a little bit of ambiguity there when we have a situation where we don't have a whole lot of data values, where we say have less than 100 data values. It can be a little bit, do we choose the left or the right boundary or the midpoint? There's a little bit of an ill-posed problem issue there. But that aside, we said, okay, we can figure out a percentile based on some strategy, pick left endpoint, right endpoint. I prefer picking the midpoint. I think that's a better approach. And we said from the percentiles, we can define a 5-number summary. Min, the first quartile, the median, the third quartile, and the max. remember the first and third quartiles are the 25th and 75th percentiles. The median we define as the 50th percentile, and the min and max are the smallest data value and largest data value. And I kind of mentioned that, sometimes we might include the deciles, D1 and D9, the 10th and 90th percentile in here. Sometimes they might be reported in something like a 5-number summary instead of the min and max, or maybe in addition to the min and the max. Again, there's always a balance between, there's always a balance with the amount of information you present. If I, took a data set of size 10 and presented to you 20 descriptive measures, well, I didn't really make that any simpler for you to understand, right? I made it worse. So there's always a bit of a trade-off between, how much we report, but sometimes the 10th and 90th percentiles are included as well. We also talked about the Pearson coefficient, and this was somewhat of an introduction to our discussion of outliers. So remembering all the way back to, I guess it was probably chapter 2, where we started talking about skewedness. We said an outlier is, well, it's a data point that just kind of doesn't fit in with the rest of the data. That's very subjective. We said, okay, well, we could talk about skewedness. We can say if a graph looks left skewed or right skewed. Well, if it's left skewed, if it has a tail to the left, that means it has outliers to the left that are not balanced by outliers to the right, and vice versa. So we said, if skewed, then outliers. So in other words, if we're left skewed, by definition, that means there has to be at least one left outlier. If we're right skewed, there has to be at least one right outlier. But notice, this doesn't necessarily find all outliers, right? We could have outliers on both sides. And if they're symmetric, we won't be skewed, but there could still be outliers. Furthermore, we said, well, if we're right skewed, obviously the max is an outlier by definition of skewedness, but what about the second largest data value? What about the third largest, fourth largest? Are they outliers? Well, we really don't know. There could be one big right outlier, or there could be, 10 of them in a data set of size 100 or something. But at least this is a place to start. So looking at the picture is a little more objective, but still fairly subjective to say if there's skewedness. And we developed a metric then, the Pearson coefficient, 3 times the mean minus the median over the standard deviation. And we compared this to plus or minus 1. We said if this metric is bigger than 1, that's evidence of right skewedness. If it's less than -1, that's evidence of left skewedness. If it's between -1 and 1, that's a lack of evidence of skewedness. So that's one way to look for the presence of outliers, is to investigate skewedness. If we see a skewedness in one direction or the other, we know that there's at least one outlier. All right, so we had finished talking about Pearson coefficient, and we said if the Pearson coefficient was bigger than 1, evidence of right skewedness, less than -1, evidence of left skewedness. Skewedness implies outliers. But we want to do a bit better. So this is about where we left off last time. So we want to do a bit better. Number one, we want to be able to detect outliers if they're symmetric, if there's not skewedness. That's one issue. And another thing is, maybe we do see right skewedness, but we ask, how many right outliers are there? Or maybe there's 3 or 4 right outliers and 1 left outlier. That's a possibility, right? Preponderance of outliers on the right, but maybe there's one hiding on the other side as well. So it's a little bit similar to like the range versus the variance, right? The range just kind of looked at the extremes, and the variance looked at every single data point. And we want to come up with something like that here. So we want to come up with an idea that will look, in a sense, at every single data point, and we can assess each data point to decide whether or not it's an outlier. And we basically have two methods of doing this. I mean, there's lots of methods of doing this, but there are two pretty common methods. And so the first method, the kind of simpler method, is the two standard deviation method. And the method essentially, and sometimes in some fields, they use 3 standard deviations instead of 2 standard deviations. We're going to use 2 standard deviations here. I think it's a little more common, but the 2 or 3 standard deviation method. If you've done, chemistry labs, those kind of things, or physics labs, and you take a bunch of repeated experiments, and before you calculate whatever your outcomes are, you want to see if you have outliers, because that might be an indication that maybe you were just a little, fast or slow on the stopwatch or something like that, or something went a little wonky with the measurements or something like that. You might look for outliers. And if you see any outliers, you might get rid of those from your data before you move on to the next step. This is something that's, somewhat common in, say, a chemistry lab, physics lab, something like that. And a lot of times they would use a method like this to determine those outliers. And the method goes, any data point with a value more than 2 standard deviations from the mean is an outlier. And we actually kind of do see the z-score pop up here again. So if we went through and for each data point or each data point's value, we computed the z-score. If the z-score is bigger than 2 or the z-score is less than -2, we call that an outlier. So one way to approach this is to take each data point, take each value, compute the z-score, and look for any z-scores that are bigger than 2 in absolute value, indicating that that data point has a value that's more than 2 standard deviations from the mean, and then we call it an outlier under this method. Another approach, you get the same answer, but another way to figure this out would be to figure out what the mean is, figure out what the standard deviation is, and then construct a lower bound and an upper bound. The lower bound being the mean minus 2 standard deviations, the upper bound being the mean plus 2 standard deviations. And then we would say that any data point with value less than the lower bound or bigger than the upper bound is an outlier. And this is kind of the way that we're going to think about this rather than the z-score method. We'll see that this ties in a little better to the next method that we're going to talk about, this idea of constructing a lower and upper bound and saying that anything between those bounds is kind of a non-outlier data point, and anything outside of those bounds is an outlier. But again, hopefully you can see that, remember, the z-score was just the number of standard deviations away from the mean that a certain data value is, or maybe I should say the number of standard deviations above the mean that a certain data value is. These are 2 equivalent ways of searching for an outlier under this method. Okay, so if we think about this method for a minute, though, so let's suppose that I have a number line here. I have some data points. Right, nice data set. No outlier, seems pretty reasonable. What's X bar going to be? Maybe I'll do this in black. Maybe X bar is something like here. What's a standard deviation going to be? Maybe a standard deviation is like that distance, so that we have basically X bar plus or minus 2 standard deviations. As kind of an aside, what's the rationale for picking X bar plus or minus 2 standard deviations? Why not 1.5 or 3 standard deviations? Remember the range rule of thumb. The range is about 4 standard deviations, or from the max to the min is about 4 standard deviations. So that's kind of what we're, in a sense, using here. Or our empirical normal rule, where we said that for a roughly bell-shaped distribution, about 95% of our data points have a value within 2 standard deviations of the mean. Okay, so let's think about then, what if I had this data set, but then I threw in, say, a big right outlier here? I think we would all agree that this red point way off to the right here is an outlier. But then what's the effect this outlier is going to have on X bar and on S? Well, we know that X bar is moderately affected by outliers. So my new X bar with this red outlier data point plugged in here is going to shift quite a bit to the right. The X bar is going to, in a sense, chase that outlier. What's going to happen to my standard deviation? Well, remember that outliers disproportionately affect variance in standard deviation. We saw in the salary data that the contribution from that salary of 100 was something like 10 times the size of the contribution of the variance from any of the other data points. Because of that squaring process, outliers disproportionately affect variance and therefore standard deviation. The new standard deviation is going to be much, much larger. So where before X bar plus 2S was something like here, what's our X bar plus 2S with these green data points plus the red data point? Well, X bar got pulled over towards that outlier, it got shifted to the right, but my standard deviation is also much larger now. So my upper bound is, in a sense, chasing the outlier that it's trying to detect. The same would be true if I had a data point or two way off on the left and not on the right. So if I have skewedness, both X bar and S, in a sense, chase the outliers with my bounds. But I want my bounds to be kind of like anchors, and I want to determine outliers based on bounds that are kind of standing still and not essentially chasing the outliers, if that kind of makes sense. What if I had symmetric outliers? Well, then X bar wouldn't be chasing the outlier so much, but the standard deviations would still be getting big. And then both of my bounds would be getting wider and wider. So in the presence of outliers, the interval that I would consider, quote, normal data gets bigger and bigger and bigger, and in a sense tries to include the outliers as normal data points. That doesn't seem great, right? If I'm searching for the presence of outliers, I don't want to use a measure or measures that are strongly affected by outliers. If I'm looking for outliers, I want to use measures that are essentially independent of outliers, that aren't affected by outliers. So that's the downside of the two standard deviation method. The upside is that we kind of already know what X bar and S are. We can crank those out in Excel, especially super easily. we can just find a z-score for each data point, or construct lower and upper bounds and check against those. So the upside is that this is a fairly simple and straightforward extension of what we've already done, right? Pretty straightforward stats. And I don't at all, just to be clear, I don't at all fault the physics or chem folks for using such a method, right? I mean, their job is not to teach a stats course. Their job is to teach you enough stats that you can, understand the experiments and evaluate your results. And I think this is fine for that. But the question is, we're in a stats course, could we do better? And I think the answer is yes. How can I construct a method for finding outliers that has the feel of the true standard deviation method? This kind of feels like the right thing to do, to set up a lower and an upper bound that are that kind of encapsulate where most of the data ought to be, and then check against that lower and upper bound to see if any data points have a value outside of that interval. How can I set up a similar method, but using measures instead of ones that are affected by outliers, using ones that are robust to outliers, as we might call them, ones that are unaffected by outliers? Well, this is where the 1.5 IQR method comes into play. Sorry that we don't have more fun names for things in math and stats. We often have boring, descriptive names for things. So this is the 1.5 IQR method. And this, I would say, is probably the standard method in things like stats programs like R or SAS or S plus or something like that. If you just tell it, hey, find me the outliers, it's probably going to use this method. So what is the 1.5 IQR method? What's the idea? Well, the idea is to replace X bar, which is a measure of center that is affected by outliers, with, well, maybe something like the median. We're not going to quite use the median, but, we're going to think but we're in a sense replacing it by the median, but we're really going to be using quartiles. We're really going to be using the first and third quartile. And that's what the Q here stands for. Stands for quartile. We're also going to replace S, a measure of variation, by a different measure of variation that is unaffected by outliers. And that different measure of variation is called the IQR, the interquartile range. So let's start by talking about what is the IQR, the interquartile range. So the interquartile range, it's a measure of variation. So in some sense, it kind of belongs to section 2, section 3.2. But the IQR is Q3 minus Q1. So because it uses quartiles and percentiles, we need to wait till 3.3 to introduce it. So it's a range, and then it's something like a max minus a min, but it's a range with respect to the quartiles, Q1 and Q3. It's the difference between Q3 and Q1. In other words, it's the distance between the first quartile data value and the third quartile data value. This is a measure of variation. So it's a little bit like, say, something like a standard deviation. Note that the quartiles are just data values, so they obviously have units of the original data. So the IQR also has units of the original data, just like we would want for any measure in section 3.1 or 3.2. Let me just check something here really quickly. Okay. I also have, it's been an absolutely crazy morning. I also have a tech person from CCAC who needs to remote into my computer, my CCAC laptop, which is not the one I'm on right now. And do something for their inventory system on that one. So I'm like, I feel like I'm multitasking this morning quite a bit. Okay, so the interquartile range is the measure of variation that we're going to use. Note that it shouldn't be affected by outliers, right? If we had, say, right outliers like this, for it to, in a sense, cut into the third quartile, the 75th percentile, we need to have 25% of our data out here as, quote, right outliers. But if we have 25% of our data way out to the right, it's kind of hard to say that that data no longer fits with most of the data. I mean, it's kind of contending for being where most of the data is. So I can't really have 25% of my data all being outliers. So Q3 kind of chops off the top 25%, and Q1 similarly chops off the bottom 25%. So Q3 and Q1 ought to be unaffected by outliers. We now have a measure of variation that importantly is robust to outliers. Okay, so we need something like a measure of center that is also robust to outliers. We might be tempted to use the median. And to be completely honest with you, I don't know why we don't just use median plus or minus 2 IQRs. But, folks that are a lot smarter than me have decided that the better way to do this is to construct a lower and an upper bound by taking one and a half IQRs away from, whoops, I need a minus on that first one. By taking one and a half IQRs away from kind of this Q1 to Q3 interval. So the lower bound is Q1 minus one and a half IQRs. The upper Q3 plus one and a half IQRs. So what does this look like? We have our median here that we're not really going to use for this calculation. We have, say, Q3 and Q1 that are not necessarily symmetric about the median. And we have this distance, which is an IQR. This is analogous to our standard deviation up above. If I go Q3 plus 1.5 IQRs, and Q1 minus 1.5 IQRs, this gives me a lower and upper bound. And note that in between Q3 and Q1, I have 1 IQR. So my lower and upper bound are a total of 4 IQRs apart. They cover a 4 IQR swath of the real line from lower to upper bound. This is similar to how my true standard deviation method covers a 4 standard deviation swath of the real line. So this has the feel of this is, kind of like a 4 IQR swath of the real line. And this is like a 4 standard deviation swath of the real line. It has the feel of the 2 standard deviation method, but with the huge benefit that all of the measures that I'm using are robust outliers. In the presence of outliers or the absence of outliers, they sit there like anchors. I don't want a method, or I would prefer not to use a method where my lower and upper bounds, the criteria that I'm using to judge the outliers, in a sense, chase the outliers where they're strongly affected by the outliers. By using the 1.5 IQR method, that gives me a method that is not affected by the outliers. Okay, so let's take a look at the Chapter 3 Excel demo. So let me switch my share here. So in these tabs at the bottom here, you see that we have like the data sets for the for our 3.1 and 3.2. You can tab over, and we didn't talk about some of this. Some of this is just extra stuff that we didn't quite get to. But we see the outlier data sets tab has Challenger mission flight times and car crash head injury criterion data. We have these two data sets, and we're going to investigate them for the presence of outliers. Now, if we look at the Challenger mission flight times, just glancing at it, I think just about everybody who knows what an outlier is would agree that the 1 minute flight time, the Challenger mission that exploded, that's an outlier. You know, you look at all of these that are like 7,000, 8,000, 12,000, and then we have one data point that has a value of 1. I think everybody would agree that's an outlier. Let's see if our tests pick that one up. So let's look at the Pearson coefficient of skewedness. So first, let's go ahead and maybe name this data set. I'll just name it CHALL for Challenger. And let's compute our 3.1 and 3.2 metrics here. STDEV dot, and we're calling this a sample, so we'll say S of the Challenger data. I need the range, which is the max minus the min. I need the mid-range, which is max plus min over 2. I need the average and the median. So the first thing, if I look at my measures of center, the mid-range, the mean, and the median, I see a mid-range of about 6,000, a mean of about 9,000, a median of about 10,000. I do see that the mid-range is less than the mean and the mean is less than the median, maybe indicating less skewedness. Is 6,000 versus 9,000 versus 10,000 far enough on the scale of something like 10,000 for you to consider that a large difference between the mid-range and the mean and between the mean and the median? That might be a little bit subjective, but you know, this certainly is lining up in the right way to indicate less skewedness. What about the Pearson coefficient? 3 times the mean minus the median over the standard deviation. The Pearson coefficient actually gives me about negative 0.95. Remember, if this was less than -1, I would say that's evidence of less skewedness. If it was between -1 and 1, I say that's lack of evidence of skewedness. And I mean, if we wanted to be like real sticklers, this is not less than -1, but practically speaking, this is pretty darn close to -1. This is kind of like maybe some evidence of less skewedness, maybe not. It's a little hard to tell, right? Again, that's where statistics and kind of the more pure math fields like algebra and calculus and stuff differ a little bit, is we're really looking for weight of evidence in favor of one claim versus another. So, I mean, a Pearson coefficient that's quite close to -1 is maybe a little bit of evidence of left skewedness. One that's like -1.2 would be a little more evidence of left skewedness. -2.3 would be, strong evidence of left skewedness. So it's a little less black and white than maybe in some fields, some other fields of math. Okay, so it looks like maybe some left skewedness, indicating a left outlier, but the skewedness metrics are maybe not so clear here. So let's look at our two standard deviation tests, and let me retype these in. So for my two standard deviation test, the idea is I want to create a lower and an upper bound. That's the mean minus or plus two standard deviations. So I want my lower bound to be the mean minus two standard deviations. And I want my upper bound to be the mean plus two standard deviations. And maybe I'll go in here and just make these whole numbers so they're just a little easier to read next to one another. So I see a lower bound of 2046 and upper bound of 15,905. Under the two standard deviation test, any data point with a value less than 2046 or bigger than 15,905 would be considered an outlier. The two standard deviation test does conclude, since one is less than 2046, the data point with value 1 is an outlier. Okay, so let's look at our 1.5 IQR method. Well, here we first need to find Q1 and Q3. As a side note with quartiles, we could use something like the percentile, one of the percentile functions in built into Excel. One of the issues with the percentile function, though, let me just jump back really quick to our previous discussion on percentiles. One of the issues with percentiles, if you remember this picture, we said it was kind of, arbitrary in some sense how we chose to assign these percentiles on each of these intervals. Something like Excel, what it actually will do is it'll do what's called interpolation. It'll do something like this. It'll kind of connect these dots with lines that are not, it'll connect them with lines that are, or actually I might have, this isn't quite right. This isn't quite exactly how Excel will do it, but it'll connect them with straight lines that are not flat. So Excel's way of calculating percentiles is a little bit more sophisticated. I wouldn't say that it's more correct. It's just, a way to make a decision on how to do the mathematical modeling. That's not the way that we're making that choice, and it's not the way the book is making it. It's a decent bit more sophistication for a relatively small payoff. So, for a course like ours, in basically any intro textbook that I've ever seen, they don't talk about this. But Excel does this thing called interpolation. So we're not going to use Excel's built-in function here. But what we're going to do is we're going to find the number of data points. We see there are 10 data points here. I could have just counted them, but if I needed to, I could use the count function. And I'm just going to come over here and really quickly do a percentile calculation. If I have 10 data points, my first tick mark is going to be at 10%, my next at 20%, my next at 30%, my 25th percentile, Q1, is going to be my third smallest data value. So Q1 is going to be the data value associated with this data point. It's going to be 8709. That's going to be Q1. So maybe I will, can I highlight this? Yeah. Note that my data values are already in increasing order. Third from the bottom is Q1, the 25th percentile, because 8709 would kind of own the land from 20% to 30%, and that's where 25% lives. By symmetry, the 75th percentile is going to be the 1, 2, it's going to be the third down from the top. That's going to be the third quartile, the 75th percentile. So Q1 is going to be this 8709, and Q3 is going to be this 11,445. Again, if you used Excel's built-in percentile functions, you would probably get a different answer than these, or different answers than these. And that's just because Excel is using a slightly more sophisticated way of estimating percentiles, right? Really, this is all a question of how specifically we define percentiles, and when we're going from a population to a sample, we're constructing an estimator, and what are the costs and benefits of using one estimator versus another. So the way we chose to construct the estimator is just a little bit different than Excel's built-in version. The IQR is the difference between Q3 and Q1. So Q3 minus Q1. The IQR is about 2,700. And this is kind of the measure of variation that's analogous to the standard deviation, but not affected by outliers. We can see that the standard deviation, which is affected by outliers, and we kind of think that one is an outlier, the standard deviation is quite a bit larger than the IQR. In this case, it's somewhere in the ballpark of 25% larger. It's affected by that outlier. I need to figure out what 1.5 IQRs is to add that to the third quartile and subtract from the first. So 1.5 IQRs is just above 4,000. And then I construct my lower and upper bound for the 1.5 IQR method by taking the first quartile minus 1.5 IQRs, and by taking the third quartile plus 1.5 IQRs. So we see again, we get a lower and upper bound of somewhere in the ballpark of 4,600 to 15,500. We see that the 1.5 IQR method would call all of these 9 data points non-outliers, and it would indeed call the data point with value 1 an outlier. So in a case like this, where it's pretty clear, both came to the same conclusion, but notice that the lower bound for the two standard deviation test was much lower. It was 2,500 points lower. It was about half the size of the lower bound for the 1.5 IQR test. Even though their upper bounds were about the same. Because we had some skewedness here, the upper bound is about the same because X bar, the mean, is kind of pulled down a little bit. It's pulled down closer to the outlier, down to the left. But then the standard deviation increases, so that kind of offsets as far as the upper bound is concerned. So ironically, in a sense, the two standard deviation test is more stable. If there are outliers in one direction, two standard deviation test is more stable for the bound that is not in the direction of the outliers, and it's more unstable. Well, it's more unstable in the bound that's in the direction of the outliers if they're only on one side. So we can imagine if this one was closer, well, right, if it was less of an outlier, we see that we start to get better concordance between these lower bounds. Right, if it was less of an obvious outlier, this lower number, then our lower bounds start to look, closer to one another between the two tests. So in the absence of outliers, the two standard deviation test for finding outliers works well. And in the presence of outliers, it doesn't work. It doesn't work as well. So that's why we would rather stick with the 1.5 IQR method. And of course, as I was adjusting this lower number here, of course, the 1.5 IQR method, its lower bound 4605 doesn't change at all. It doesn't care about that that minimum data value at all, because that's below the 25th percentile. Are there any questions so far on any of this? Okay, let's do the same thing for the car crash head injury criterion data. So I'll select my data and I'll just call it HIC for head injury criterion. And we'll go through and compute our descriptive stats here. Okay, so looking at our descriptive stats, we have a mid-range of 435, a mean of 430, a median of 393. Well, the mean does seem to be a decent bit above the median, maybe about 10% larger than the median. The mid-range 435 is a little bit above the mean, but only maybe a percent or so larger. These do line up in the correct way to indicate maybe some right skewedness, but do I think that these are far enough apart to be evidence of right skewedness? I'm not sure. Let's look at the Pearson coefficient for something a little more objective. So this is 3 times the mean minus the median over the standard deviation. Pearson coefficient here is about 1.25, 1.26, indicating some right skewedness and suggesting that at least we had one right outlier. That's what's suggested by the Pearson coefficient. Question in chat, let's see. No, that's no problem. Yeah. If you need to pop out of class, not a problem at all. We do see a Pearson coefficient indicating some evidence of right skewedness. We did see that the measure of the center kind of lined up in the way that might be indicative of some right skewedness. If our data set is right skewed, then we have to have at least one outlier. So this skewedness evaluation suggests that at least this highest number is an outlier. But it really doesn't say anything about, if is 544 an outlier, what about 520? What about 501? Even if we, really had set in our minds that this is definitely right skewed, we would say, yes, 544 is an outlier, but we wouldn't know about these ones. Okay, so let's look at our two standard deviation test. The lower bound is the mean minus two standard deviations. The upper bound, the mean plus two standard deviations. And let me just change these really quick to make them look the same as my data. So my two standard deviation test actually says a data point is an outlier only if its value is below 253 or above 608. I don't see any data points with value below 253 or above 608. The two standard deviation test indicates no outliers, even though the Pearson coefficient and to some extent the measures of center indicated at least one right outlier, perhaps more right outliers. So we have some disagreement between our different perspectives here. For something that's, number one, a little more objective, and number two, a little more robust to outliers, let's go to the 1.5 IQR method. Let's use it as kind of the something like the tiebreaker here. Okay, so how many data points do I have? I have 7 data points. I have 7 data points, so 0 sevenths, 1/7 is about 14%. 2 sevenths is about 28%. I need to find Q1. Q1, the 25th percentile, is between 14 and 28%. So Q1 is going to be the second smallest data value. So this is Q1. The second largest is going to be Q3 by symmetry. My IQR is going to be the difference, Q3 minus Q1. 1.5 IQRs is just 1.5 times that number. So this is the thing that's analogous to the standard deviation. This 246 is kind of in that, or I'm sorry, picked the wrong one. This is analogous to the standard deviation. This 164 is kind of analogous to the 88.7 as a measure of variation. Then my lower and upper bounds are going to be, my lower bound is Q1, the left end of that kind of middle 50% of the data, minus 1.5 IQRs. My upper bound is going to be Q3 plus 1.5 IQRs. I see that my 1.5 IQR method also indicates no outliers. Right. I don't have any data points with value below 110 or with value above 766. So in this case, I'd be more confident saying no outliers and rejecting skewedness here. That's probably where I would go. I'd probably say, okay, I mean, these measures aren't going to be great when I have such a small data set, when I have only 7 data points. So I probably would be a little more skeptical of my Pearson coefficient being above 1 and claiming right skewedness and claiming a right outlier, when my 1.5 IQR method and even the 2 standard deviation test don't indicate any outliers. Any questions on any of this? So in this case, what's kind of What seems to me that's happening is we have kind of a cluster of data that's in, say, the 300s and a cluster that's in like the 500s. And so we almost have like bimodal data, right? So this is kind of one cluster and this is another cluster. So in a sense, maybe kind of some of our methods are picking up that second cluster as being quote outliers, but other methods are saying, no, it's really just kind of two clusters, right? Now, which method is best or is correct or something like that. Again, all of this is somewhat of a gray area because why are we looking for outliers to begin with? Maybe if we're in a physics or chemistry lab, we're looking for outliers because we think that occasionally, if I start and stop a stopwatch, occasionally just by human error, I get distracted or something, I'm going to be a little fast or a little slow on the stopwatch. And that's not going to be really an accurate indication of what actually happened in an experiment. Those are the kind of things I'd like to remove from the data, right? So maybe if I had a specific purpose like that, maybe I could investigate it a little more closely and say, do I want to be a little more likely to throw out a data point? Do I want to be a little more likely to include a data point if it's on the boundary? What am I doing with the outliers? Why do I care about the outliers? So, but again, a little more gray area here than in something like, say, algebra, where the answer is the answer and that's the end of the story. Okay, so any questions on outliers, either related to skewedness or related to finding outliers with two standard deviation method or the 1.5 IQR method? All right, and then the last uh, little thing for today is the 5-number summary and its relation to box plots, or sometimes called box and whisker plots. Remember, the 5-number summary was the minimum, Q1, the median, Q3, and the max. So let's take, for instance, the salary data here. And let's figure out the 5-number summary for the salary data. Well, the minimum is 25. The max is 100. If I rewrite these in increasing order, 25, 3/28, 30, 55, and 100. I see the 28 as the median. And I have Q1 and Q3. Well, I see that there are 7 data points. The first is going to go from 0 to 14%. The second from 14 to 28%. This is going to be Q1. The second lowest is going to be Q1. That's going to be 28. The second highest then is going to be Q3, 55. And if you wanted to write out the percentile chart, no problem. Go ahead and just write out the chart, and only takes a couple more minutes. Now for a box plot, what I do is I set a number line. I indicate on the number line the min, Q1, the median, Q3, and the max. And then above the number line, I make a vertical tick mark above each of those. The middle three, encapsulating Q1, the median, and Q3, I draw a box. I draw a horizontal line connecting the tops of those three and the bottoms. And then going from that rectangle out to the extremes, the min and the max, I draw what's often called a whisker. Just this kind of, single line coming out in each direction. So you might have seen these in journal articles. A lot of times data is presented this kind of a way in journal articles. So this is the idea of a box plot or a box and whisker plot. If I want to make a box plot for the salary data, I see my min is 25. I do want to stick to a pretty decent scale here because I want the size of my whiskers relative to the size of the box and the location of the median inside of the box to be reasonably accurate. So I'm going to try to stay pretty accurate here. Maybe I'll go 25 to 40 to 55 to 70 to 85 to 100, something like that. So I see a min at 25, my max at 100. Q1 and the median are actually both at 28, and Q3 at 55. So this is kind of a funny box and whisker plot because the median is all the way at the left of the box. But if I see something like this where the median is all the way at the left of the box and where my right whisker is way longer than the left whisker, that's kind of suggesting to me that there's maybe a bit of right skewedness here, maybe some outliers on the right. If I looked instead, sorry, if I looked instead at the tax return data, let's just pick the Ashley data, which we know ought to be pretty nice and symmetric and well behaved. Her 5 data points are 5, 7, 8, 9, 11. And actually, when we have 5 data points, the 5-number summary turns out to just be those 5 numbers. Pretty clearly, the min and the max are the min and the max, these numbers. The median is the middle one. And if I have 5 data points, then what are the percentiles? The lowest data value corresponds to the 0 to 20th percentile. The next one, 20th to 40th percentile, the 25th percentile, the first quartile is there, and Q3. So if I actually have a data set with 5 data points, those 5 data points put in order are just the 5-number summary as well. It just turns out that way. So if I make my box and whisker plot now, five is my min, 7 is Q1, 8 is the median, 9 is Q3, and 11 is the max. Again, I was trying to be, reasonably accurate with the scale. It's not going to be perfect, but I want it to be a pretty decent scale. I connect my middle 3 vertical tick marks with horizontal lines to make a box. And then I make my whiskers. And I see, as opposed to the salary data up here, where the right whisker was very long relative to the left whisker, and the median was all the way at the left side of the box. Here, the median is right in the middle of the box, and my 2 whiskers are about the same length. It seems like this data set is pretty nice and symmetric. And if you remember that the mean is equal to the median, which is equal to the mid-range, that also is very indicative of being symmetric. Note also that the width of this box is actually 1 IQR, right? Because this is Q1 to Q3. So if I went 1.5 more IQRs, IQR to the right of the box and 1.5 more IQRs to the left of the box, I see that that encapsulates all of the data from the min to the max. There don't seem to be any outliers here. For the salary data, I mean, there don't seem to be any low outliers because certainly if I went 1.5 of these to the left, the min is not going to be less than that. But I don't know. I think I'd have to run the numbers on this because I feel like this is going to be pretty close, right? I don't think it's going to be clear enough based on just my little sketch here to make a call whether I think this that 100 is an outlier or not. And lastly, one minor note is occasionally what you'll see is something like this. You might see something like this. This is another style of writing a box plot where min and max are taken to be the smallest and largest non-outlier values. So this would be the minimum non-outlier and the max non-outlier value. So in some circumstances, what folks will do is they'll go through and take the data set, first go through and use something like the 1.5 IQR method, find the outliers if there are any. If there are outliers, kind of exclude them from making the box and whisker plot. Make the box and the whiskers based on the non-outlier data is really just the min and the max using the non-outlier data set. And then indicate the outliers with dots separately from the box and whisker plot. What's the benefit of that? Well, if I have a box and whisker plot up here, let's just pretend that it was a little more extreme to make it a little more clear. Okay. So now, I mean, this is definitely an outlier. I don't think there's any question to that. But if I just glance at this box and whisker plot, is there one outlier? Is there two, or are there a bunch? I can get a little bit more information on the graph by reporting maybe something like this. Showing me that, okay, it seems like there are 3 right outliers, and the non-outlier data, this is what the box and whisker plot looks like. I don't necessarily think that one way is better or worse than the other way. It's a question of what you're trying to convey. If you're really interested in the outliers and knowing whether there are any and how many there are and so on, the dots method is probably better. If you're not so interested in the outliers, then just the standard box and whisker where the whiskers go from max to min is probably fine. Are there any questions on anything in chapter 3? So I know that chapter 3 was a big chapter, a lot of information. Also got a lot more technical than chapters 1 and 2, a lot more calculation and so on. But any questions on any of this? Okay, let me switch my screen over then to the chapter 4 PowerPoint. So I'll bring up chapter 4 PowerPoint part 1. Get that started up here. And we'll start chapter 4 today. Again, continue on with it in the supplement. And then continue on further next week. Okay, so chapter 4, we're starting into the topic of probability. And kind of having wrapped up chapter 3, I like this quote by Mark Twain that where he says facts are stubborn things, but statistics are more pliable. And now that we see how much gray area there is in choosing a measure of center, a measure of variation, or a graphical technique or whatever, maybe we see what he is talking about here a little bit. So section 4.1 deals with the basics of probability. Now there's a really important transition that happens here. There's, in a sense, kind of like three phases to this course. Most math courses, if you are in an algebra course or something, it's just one topic builds on the next, pretty much straight through the course. It's pretty much just, building up like a house or something from the foundation up to the roof. But in a course like this, again, we're making judgment calls. We're, using mathematical techniques, certainly, but we're also deciding what techniques to use and when. We're kind of moving from a phase from chapters 2 and 3 where we were talking about descriptive techniques, where the goal was to come up with ways to take raw data and make it more meaningful, more understandable to the person we're presenting it to. Chapters 4, 5, and 6 really kind of take a completely different point of view. They say, okay, well, let's build a mathematical structure. Chapters 4, 5, and 6 are much more like, say, an algebra course or something. We're building an underlying mathematical structure, in some sense, kind of from the ground up. And you say, well, this seems like wholly unrelated to what we just, spent a month doing in chapters 2 and 3. Why are we doing this? Well, the reason is that when we get to chapters, say, 7 and 8, and some of the chapters after that, we're really going to need this additional mathematical structure to set a firm foundation for those concepts. So we now have an idea of how data sets work, of how data crunching works, of how some of these different ideas of outliers and looking for outliers, things like that. We have a general idea of how that works. We're now going to kind of set that aside for a minute, come over to a different idea, and that is building a mathematical structure. And then chapters 7 and 8 really tie the two ideas together. They tie together the ideas in a way that hopefully we're going to get more out of it. Hopefully we're going to not just go from data to something like information, like a mean or a standard deviation, but actually move up another level to something like knowledge. Can we make inferences? Can I take a small piece of a small data set from the world, a small experiment from the world, a small piece of understanding about the world, and extrapolate and say something that is outside of what I have direct access to, right? Can I take those 10 times that I rolled the ball down the slope and measured the time in a physics classroom, and can I say something about how gravity works in general, right? That's kind of the idea of chapter 7 and 8 is we understand the data side of things now. We're going to build the mathematics side, and then we're going to tie the two together and hopefully come up with something that's a lot more powerful and a lot more useful for understanding the world. So we're switching now to the building the mathematical structure part. And the first part of this is chapter 4, talking about probability, 4.1 talking about the basics of probability. So probability, roughly speaking, is the chance of an event occurring. And we're typically trying to answer one of two questions. Maybe what's the expected outcome of an activity? So if I do this activity, what do I think is likely to happen? Or maybe what's the risk of an activity? If I do this activity, what's in some sense the range of reasonable situations that could occur? A probability experiment is a random process that leads to well-defined results called outcomes. So we can ask a question here, and I think it's a fair question, is what do we mean by a random process? And I mentioned this a little bit at the beginning of the course. I'm going to mention it again now. I'm not going to go too deeply into it. But the question of what does probability actually mean in the real world is an incredibly deep question. It's a very philosophical question. It's not a question that can really be answered mathematically. So, I mean, if I say there's a 30% chance that it will rain tomorrow, what does that mean? Uh, some people might say that means that on, you know, if there were 100 days, kind of like today, where I have a forecast of, say, a 30% chance of rain tomorrow, that if I went through those 100 days and I looked back, I would expect to see that on 30 of those days it rained and on 100 it didn't, or sorry, on 70 it didn't, 30 it did, 70 it didn't. That's what I would expect to see. Some people would say, well, 30% represents a degree of belief that I have. I mean, I don't get to live tomorrow 100 times. I get to live tomorrow once. If I decide to go on a picnic tomorrow, well, it's either going to rain on my picnic or not. It's a degree of belief that affects my decision making. That's a different perspective. So there's, once we try to take this idea of probability and tie it to something very tangible in the real world, that's a big philosophical debate, what it means. However, what I don't think anybody really debates about, unless they're just being ornery or don't know what they're talking about, is this sense of probability, in the sense that when we're building the mathematical structure and just looking at the mathematical structure, then we can say what probability means very clearly. So if I try to take this mathematical structure and overlay it onto the weather and the real world and try to decide whether I should go on a picnic tomorrow, that's how to appropriately overlay the mathematical structure onto the real world and what that means and all what can be determined from that and everything. Big question. Lots of debate on that. It was really a question of philosophy rather than mathematics. But as far as what does the structure look like, that's a very mathematical question. And that's the question we're going to be focusing on here. So a random process is simply one where the process follows these rules of probability. If we wanted to kind of have something to kind of think about, usually we talk about probability experiments being things like die rolls or drawing a card from a deck or flipping a coin, because those are pretty tightly controlled systems, right? Something like the weather is very complicated. Something like rolling a die, it's like, okay, I throw the die and it comes up 1 through 6 equally likely. Now, could somebody balk at that and say, oh, well, under Newtonian mechanics, if you know this and know that and can predict this and that, maybe when the person lets go of the die, you could predict whether it's going to come up 1, 2, 3, 4, 5, or 6, maybe. But for our purposes, we're saying at the very least, the systems we're interested in are sufficiently chaotic. They're sufficiently hard to determine on the basis of, physics or something like that, that it's essentially a crapshoot in almost a literal sense. When I roll a die, it's going to come up 1, 2, 3, 4, 5, 6, equally likely. And I have really no idea when I let go of the die, which one it's going to come up. So that's the sense in which we mean random. We mean it's sufficiently hard for me to predict that I don't even try to predict it. And I just, treat it under this mathematical model of randomness and probability. But these experiments result in outcomes. So if I rolled a die, maybe an outcome of rolling a 6-sided die could be getting a 1 or getting a 4. The sample space is the set of all possible outcomes of a probability experiment. And I do mean all possible here. Again, this is a mathematical model, so we can say the only thing that can happen when we roll a die under this model is it comes up 1, 2, 3, 4, 5, 6. It never lands on its side. It never, falls down the drain and we can't tell what it is. It always is going to come up 1, 2, 3, 4, 5, 6. That's our model. Now, if we tried to apply this to the real world and you said, well, this model doesn't cover the case where you roll the die and it lands on its side, okay. But that's the George Box quote, right? Is all models are wrong, some models are useful. Is it useful enough to be applicable in this situation? Maybe, maybe not. But from the standpoint of the mathematical model, we can enumerate all the possible outcomes and say, this is the model. An event consists of a set of outcomes. So an event could be like rolling an even number or rolling a number bigger than 1 or something like that. An event could even consist of no outcomes. An event could be rolling a number bigger than 8 on a 6-sided die. There simply aren't any outcomes 1, 2, 3, 4, 5, 6 that are bigger than 8, but that's just an event that doesn't have any outcomes in it. So again, some examples: probability experiment rolling a die. The outcome is the number we get when we roll the die one time. Sample space 1, 2, 3, 4, 5, 6, and some events down here. Another example: our experiment could be rolling a die 2 times. The outcome could be the numbers in order, so first roll, then second roll, that we get when we roll the die 2 times. So the sample space could be something like 1, 1. So this isn't an 11, but 1, 1. So rolling a 1 on the first roll and a 1 on the second roll, or 1, 2. Note that 1, 2 is different than 2, 1 because in 1, 2, the 1 came first, the 2 came second. In 2, 1, the 2 came first, the 1 came second. All the way up through 6, 6. So that would be our sample space. All of the pairings of 1 through 6 is the first number, with 1 through 6 is the second number. That's going to be 36 different outcomes in the sample space. And some possible events might be, say, rolling 2 odd numbers. So for instance, 1, 1 or 1, 5 or 5, 3. Or maybe rolling a number greater than 2 on one of the rolls. So like 1, 4 would satisfy that event, but also say 5, 6 would. At least one of the numbers I got was strictly greater than 2. I could look at an event like not rolling a 3 on either of the rolls. So 1, 2 or 2, 6 or something, but not 3, 1 or 3, 3. So I can come up with lots and lots of events, and each event will have some set of outcomes. Some events might consist of no outcomes. Some events might consist of all the outcomes, right? Rolling at least one number between 1 and 6, including 1 and 6. Of course, that's going to have an outcome that's the entire sample space. Another example, we're probably to experiment flipping a coin 5 times. And maybe we consider the outcome the sequence of heads and tails. So what was the first flip, the second, third, fourth, and fifth flip? So I could have 5 heads. I could have 4 heads, then a tail on the 5th flip. Or I could have 1 tail on the 4th flip and the rest heads. Those would be different outcomes in the sample space because I'm considering the unique sequences of heads and tails, not just the number of heads on 5 flips. That would be a different sample space. And some events might look like flipping all heads, which consists of only one outcome in the sample space. Heads, 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 heads. Flipping 3 heads, then 2 tails. One outcome in the sample space. But if I said flipping 3 heads and 2 tails on 5 flips, note that there will be a lot of outcomes to satisfy that. 3 heads, then 2 tails satisfies it, but so does 2 heads, then a tail, then a head, then a tail. I have to be very careful with the wording when I'm working with anything in probability, right? Changing then to and really changed the meaning of the event and changed the set of outcomes that satisfy that event. So I have to be very careful. All right. So I think that is where we'll stop today.